Hello, grade 12s. You're in a physical science lesson. This is a consolidation lesson of chemical equilibrium. My name is Gillian, and we're going to have a look at some of the tricky questions that pop up and really challenge us and our knowledge. So the first question is quite a big question, and it covers quite a lot of information that we should know. It says here, it sets the scene. The dissociation of iodine molecules to iodine atoms is a reversible reaction taking place in a sealed container at 727 degrees Celsius. So from that reading, we know then that we have a constant temperature at 727 degrees Celsius. We know that it is a dissociation reaction, that we're dealing with iodine molecules, and that we also have iodine atoms. They give us the balanced equation. They tell us that it's balanced, and we can see here that iodine, the diatomic iodine gas, will form iodine atoms, and that is also in the gaseous phase. It is reversible, so the reversible reaction is possible. The Kc for the reaction at this particular temperature is 3,76 times 10 to the minus 3. Kc does not have any units. It's got no units, and the reason why it has no units is because it's a comparison. It is a ratio between the concentration of reactants and the concentration of products, and that is once equilibrium has been established. Kc can only be changed when there is a change in temperature. Nothing else can change Kc. What are they going to ask us? The very first thing they ask us is, write down the meaning of the term reversible reaction. Now, this is nothing that you have, it's not a definition that you've learned, but they're asking about an understanding. So what is a reversible reaction? Well, a reversible reaction is one in which the reactants form products, and then the products can then form the reactants again. So you could say that. You could say that both the forward reaction and the reverse reaction is possible. So those are two options for you that you could use. The next question is quite detailed. They're now asking you to use your understanding and your knowledge and put them together. At equilibrium, the pressure of the system is increased by decreasing the volume. This works for a gas only. Only a gas responds to a change in volume. The temperature remains constant. So they're now going to give us scenarios and ask us how are these things going to be affected. So how will each of the following be affected? The first one is the value of the equilibrium constant. Now, we already know this. The equilibrium constant, Kc, is only affected by temperature. That's the only time it can change. Is this temperature? No, it's not temperature. It is a constant temperature. It is the pressure which is changing. So, how will it be affected? How will the Kc value be affected? It will not be. It remains the same. The second question, how will the number of molecules of diatomic iodine be affected? So, because we are changing the volume, so it was a big volume of container, we're now changing it to a little volume, it's a smaller volume. With Boyle's law, there is an inversely proportional relationship. A decrease in volume increases the pressure. In an equilibrium situation, the equilibrium will always shift to try and alleviate the number of moles, because when we're decreasing the volume and therefore increasing the pressure, the thing that is causing the pressure is the number of moles, the number of particles that is in that space. So the equilibrium will shift to try and reduce the number of molecules or number of moles that is in that particular space. Obviously, that would make sense, right? So when we've got to look at our balanced equation over here, which is I2, reacts to form 2I. So you can see that there are 2 moles of the atoms of iodine there and 1 mole of iodine, diatomic iodine. So which way is it going to shift? Well, obviously the equilibrium is going to shift to alleviate the number of moles, so it's going to shift in this way. And so what is going to happen with these, the number of iodine molecules? Well, it's going to increase. So the answer for this is increases. So the number of iodine molecules increases. That's quite a lot of thought work, right? Just for one answer. But you need to think through that so that you can get the correct answer, even if it is worth only 2 marks. Now, the next question is explain what we have just done. Explain your answer, which is the increase in iodine molecules. Explain it and refer in your explanation to Le Chatelier's principle. In our Big Ideas lesson, we spoke about this. How do we answer in terms of Le Chatelier? There are 4 things. Distress. We have to say, what is the distress? We have to say, how is the system going to respond to that distress? Which reaction is favored? And what effect will the new equilibrium have when it is reached? So let's put what we have just spoken about into words. So we've said that with an increase in pressure, the system is going to try and alleviate the number of moles. And so we're moving from 2 moles to 1 mole, and so the equilibrium is going to shift in that direction. What is the stress? So the distress or the stress here, I've just put a reminder up for us. So the distress is going to be that there is pressure that is increased because we have reduced the volume. So the stress is the pressure is increasing. What is the response? Well, obviously the equilibrium is going to shift so that it can decrease that pressure. And how is it going to do that? It's going to do that by reducing the number of moles of gas. So we write there, the system reacts to decrease the pressure by forming less moles of gas. There we go, it's forming less moles of gas. You can write decrease if you want to too. So which reaction is favored? So we're on to this one here. There, which one is favored? It is going to be the reverse reaction. The reverse reaction is favored. And once the new equilibrium is reached, what are we going to see? What is the effect of that? Well, the I2 concentration is going to increase. And what about I? Well, that concentration is going to decrease. And we write it like that. Our next question is looking at the Kc value. So I have written this equation up here again, just to keep us remembering what we're dealing with. 1.4 says that at this temperature, 227 degrees Celsius, the Kc value for the reaction we're dealing with is this value here, 5,6 times 10 to the minus 12. Is the forward reaction endothermic or exothermic? And you need to explain your answer. Now, there is a little bit of information that they gave us right at the very beginning of this question, and it was this here. Have a look at that. The Kc for the reaction at 727 degrees Celsius is 3,76 times 10 to the minus 3. So this is the initial temperature of the reaction. They're now telling us that something has happened. And what has happened is a decrease in temperature. So our temperature has decreased. How do I know that? Because we started off with 727 degrees Celsius, and the temperature is now at 227 degrees Celsius. It has decreased. What about Kc? Well, our Kc expression for this particular reaction is going to be the concentration of I squared. Remember, that comes from the number of moles, the coefficient in front, divided by the concentration of I2. So these are the products divided by the concentration of the reactants. So that is the specific Kc expression for this reaction. What is happening to the Kc value? So the first Kc value is that one there. So the Kc value is 3,76 times 10 to the minus 3. It has not got a unit because we're talking about a ratio or a comparison. It is decreasing. Have a look at that. The Kc value has dropped to 5,6 times 10 to the minus 12. So the Kc value has also decreased. It has also decreased. So if our Kc value is decreasing with this disruption, it means that the amount, the concentration of I must have decreased as well. So our concentration of product has decreased to give us a lower Kc value. So Kc, remember we spoke about this in the first video, that Kc, if it is smaller than 0, then we're talking about our concentration of products being lower. So with a decrease in temperature, the concentration of I is less. I is less. So if we drop the temperature, what is happening? That reaction is being favored. The reverse reaction is being favored. A drop in temperature means that the reaction the equilibrium has to change to create more energy, more heat. So that is the exothermic reaction is favored. And so this reaction, the reverse reaction, is going to be exothermic. But that is not the question. The question says, is the forward reaction endothermic or exothermic? So the forward reaction has to be an endothermic reaction. It is time for a break, grade 12s. I will see you just now. Hello, grade 12s. We are back from our break, and we have been busy working out which reaction is endothermic or exothermic. The forward reaction, what is that? And it was round about the equilibrium reaction of iodine molecules forming iodine atoms. Now, in this particular question, there was a lot of working out in our minds. We had to figure out what was going on. The answer is one word. It's either endothermic or exothermic. But they ask us to fully explain our answer. So here we go. How are we going to write this in words to get all our marks and to make sense to the examiner? So our Kc value decreases. We found that. It decreases with a decrease in temperature. So the Kc value, remember we had to use the initial Kc value that was hidden right on top of the page. So the Kc value decreases with a decrease in temperature. So what you observe, that's just from observation. The reverse reaction is going to be favored with this decrease in temperature. The concentration then of the reactants is going to increase, you could say that, or you could say the concentration of the products is going to decrease. Remember that our reaction was moving from iodine atoms to iodine molecules. What does that mean? It means that the yield, that means how much is made, our products, the yield is decreasing. So what is happening here? The decrease in temperature favors the exothermic reaction. So all these words are explaining step by step our thought processes in unpacking this question. And then that gives us the answer, which is endothermic. It is good to practice writing these answers down so that it is easier for you in an assessment situation. It can just roll off your pen. The next question I want us to tackle is the one that uses the Rice table. Our putting down in a structured way our calculations of a reaction in the beginning, the initial number of moles that are available, the middle, what's happening to the change in the moles as equilibrium is reached, and then at the end, when equilibrium is reached, what is the moles of each component of the reaction. And from there, we can then calculate the concentration and obviously Kc. So this is a really tricky question. It requires a lot of thought. You need to set out your work very clearly and explain exactly what you're doing. So in other words, write down your maths. It's like doing a maths exam, writing down your steps of calculation very carefully. So the question says, a certain mass of iodine molecules, I2, is sealed in a 12.3 decimeter cubed flask. That is telling me my volume. Okay, it's telling me what the volume is. At a temperature of 727 degrees Celsius, and at that temperature, they give us the constant. The equilibrium constant, 3,76 times 10 to the minus 3. When equilibrium is reached, the concentration of the iodine atoms is found to be that amount. So 4,79 times 10 to the minus 3 mole per decimeter cubed. So that is the concentration of the iodine atoms. Okay, concentration of the iodine atoms. Calculate the initial mass of the iodine molecules in the flask. Okay, so have a look at here. Molecules, the word is telling us that they are looking for I2, the diatomic molecules. So where do we start? We're going to take all this information that we've got and we're going to put it onto our Rice table. So here we've got our Rice table. Rice stands for ratio, R. The ratio, what is the ratio in the that has been formed in the equilibrium reaction? So this is the reaction. I've placed it here for you. They gave it to us at the beginning of the question. We've got the iodine molecule, diatomic molecule, reacting to form iodine atoms there. They're both gas. It is balanced. Our ratio is going to be 1 is to 2. Okay. What's the next thing? I stands for initial moles. So the initial number of moles. We have not been told anything. We don't know what the iodine molecules are, what the initial number of moles is at the beginning of this reaction. Nothing. We do know, though, that when the reaction starts, that the number of moles of product is going to be 0. So we do have that. Now, change in mole. We don't know anything. They haven't told us anything about that. So the C in the Rice stands for change in, so that's why it's delta, change in the number of moles as the reaction reaches equilibrium. And then at equilibrium, what is the number of moles? Well, we don't know that either. We do know, however, if I go back to the slide, they have told us that the don't tell us the number of moles, they tell us the concentration of the iodine atoms is 4.79 times 10 to the minus 3 moles per decimeter cubed. So that is concentration. So I can't fill anything into these two rows for now, but what I can do is I can fill in the concentration of the iodine atoms at equilibrium. What else do they tell us? This is quite a little bit of information. They do tell us the Kc value. That is one thing they do tell us. And they tell us at this equilibrium that the Kc value is 3,76 times 10 to the minus 3. We have the concentration for the product. So there is our formula. Remember, we've got an expression for every single equation reaction that we come across. It's very specific. The Kc expression is very specific for every single reaction. So there it is there. You need to write that. That's the one you need to write. And you can see that the product is squared. Why? Because there is a 2 coefficient. So we square this value, this concentration that has been given to us. We calculate it all out, and we can then find the concentration of the diatomic iodine molecule at equilibrium. So we've worked all that out, and we get an answer of 6,102 times 10 to the minus 3. It will be moles per decimeter cubed. Okay, so we're one step further. We have discovered what the concentration is of the diatomic iodine molecule at equilibrium. From our equation of concentration, we know that C is equal to number of moles over volume. We are told what the volume is. They told us it's in a flask, which is 12,3 decimeters cubed. So if we rearrange our formula, we can work out the number of moles. We say number of moles is the concentration, which we've just figured out here. So we figured that one out. We were given that one. We can work out the concentration. From the concentration, we can work out the number of moles, timesing it by the volume. So this is the volume here. And we times both concentrations by the same volume, because they're in the same flask, and we end up with an answer of this. So we've got 0,0589 moles at equilibrium for the atoms, and we have got 0,0751 moles for the molecule at equilibrium. What is the change in number of mole though? Because that is really what we want to find out. So for our product, we know that this is going to be the same value. How many moles of iodine molecules are used up? Well, we need to use our ratio. So our ratio, as we've said before, is 1 to 2. And so if we take the number of moles that have been formed through equilibrium, we divide it by 2, we can then get this answer here using the ratio. So we now have figured out the number of moles of molecule, iodine molecule, that is used up in this reaction. And that helps us because now we can work on how to find and calculate the mass, because that was the question. What is the mass of iodine molecules that is used up? So our initial number of moles is this. Once we've gone through our calculations, it's 0,1045. Now we can work with our standard equation or formula. We get this from our periodic table, not periodic table, your data sheet, which is mass is equal to molar mass times number of moles. The molar mass from the periodic table is 254 grams per mole. We times it by the number of moles that we have discovered or calculated, and we end up with this answer. So the mass of iodine molecules involved in this equilibrium reaction is 26,543 grams. That was a massive question. So, grade 12s, I hope that helps you with formulating your thoughts and thinking through these tricky kinds of questions. The rest of these answers you will find on the Yellow Ed platform. Please go and try them out and then check your answers from the answer sheet. Right, go well.